Well, hello, everybody. Welcome to the technical webinar on OpenCBDC. This is a joint project between the Federal Reserve Bank of Boston and MIT's Digital Currency Initiative. So here's the agenda for today's meeting. I'm going to be doing a simple introduction, and then I will turn it over to have a little bit more of an introduction about the DCI. Then we're going to do an overview. I'll do an overview of OpenCBDC, and then we'll do a deep dive into what we've built. This will be James Lovejoy will do that, and then we'll have an overview from Sam on the open source project, and then we'll open it up to Q&A. And again, please send questions throughout, and we'd love to answer them. Let me just quickly talk about who's here. So I am Anders Brownworth. I'm working at the Federal Reserve Bank of Boston. And let me just mention the views that I express are my views and not the views of the Federal Reserve Bank of Boston or the Federal Reserve System as a whole. That is also true of James Lovejoy, who is also on the call. Also here is Neha Narula. And she is the director of the MIT DCI. We'll hear from her in just a second. James Lovejoy works at the Federal Reserve Bank of Boston, as mentioned. Sam is at the DCI as well at MIT, and he'll be doing the open source discussion. So he'll arm us with the facts there. Very excited. And then Nikhil George will also from MIT DCI will facilitate the Q&A session at the end. So he'll be sending in the questions. With that, let me turn it over, please, to Neha Narula, the director of the MIT DCI.
Thanks, Anders. It's really great to see you all here today. We're very excited to share the work that we've been doing for the past 18 months to get this out into the public, and most importantly, to get all of your feedback and contributions and ideas to make this work even better. So I'm going to start by just giving, for those who don't know, a little bit of an overview of the Digital Currency Initiative at MIT. So we were founded in 2015. Our mission is to empower people by making it as easy to move value as it is to move information. And we work on that in primarily two different ways. So first of all, we spend a fair amount of our effort on the scalability, security, and privacy behind decentralized cryptocurrencies. So we do that primarily by writing open source software and engaging in technology research. We support several developers who work full-time on Bitcoin Core. And the other half of the work we do and the engagement with the Federal Reserve Bank of Boston and soon to be other central banks is to work on centralized digital currency. So thinking about what we can take and learn from the cryptocurrency world, what's applicable and what's not, and to think about designing new forms of digital currency that might operate in the centralized context or central bank context. The values that we usually imbue in our work are user agency. We focus a lot on giving users control of their own data and thinking very carefully about privacy. Open source, everything we do, we release open source, and rigor. So bringing MIT to the game to try to define strong benchmarks, strong comparison metrics, and to elevate the conversation around the technology. So below is just a little bit of our timeline, what we've been doing for the past 6 years, working on Bitcoin Core development with a security focus, but we have been thinking about central bank digital currency since 2016, and 2020 is when we actually began this collaboration with the Federal Reserve Bank of Boston. And so with that, I will turn it back over to Anders.
Thank you very much, Neha. That's great framing. Let me move on. Okay, so let's step to an overview of the project, OpenCBDC. I'll just give a little kind of a general overview here. So the goals that we set for this project are pretty, they're pretty nebulous. They're not very exact. We wanted to test a hypothetical central bank digital currency platform that is, of course, secure. What does that mean? That's pretty nuanced, I suppose, but generally we want it to be secure. It needs to be flexible. This is an architecture that needs to be able to test a wide variety of things. So that was key. Needs to be resilient. It's got to be able to handle failure as the norm. In the machines that implement it. It pretty much means fault tolerant geographically and up all the time. Needs to be performant. Well, what does that mean? Well, this is actually where we put a few numbers. We decided that we should hit at least 100,000 transactions a second, and the goal was to settle in 5 seconds or less. Now, the numbers actually don't matter. They just need to be, relatively high. The point here is fast. We really wanted a system that was going to be fast. So those are kind of the real benchmarks that we wanted to hit, but we really wanted to make something that was people would consider as fast. So the question is, how do you do that? Well, the best way to do that is build a really, really big computer and stick it in the basement of some building and just do it all in one giant monolithic stack. Well, as we found out about that kind of thing, the power goes out, the hardware breaks, networks go down, et cetera. So the result would be, well, what about building a network of geographically distributed components? Okay, and not too surprisingly, if you add that complexity, sometimes you have to address the issues that come out of that. So the issues that we found are, we basically need geographic distribution and low latency and global consistency. And if you try to do all three of these, they sort of are at loggerheads. So you have to balance them. Doing any two of these is relatively approachable. A lot of projects do that. But to balance the three and to do it in the context of a CDBC is a unique problem. And one that requires, I think, a lot of thought and some original research. So I mentioned the unique design requirements, right? Well, obviously, you need to prevent double spends. That's common across a lot of cryptocurrencies, but that's a big one. You need low latency finality, essentially global consistency quickly. However, Byzantine fault tolerance isn't necessarily the core problem in a centralized system like this, right? It's distributed, but it's centrally controlled. Not to say, though, that Byzantine fault tolerance is not, something you would be interested in. It very well may be, but it's not the core issue. And that leads to this system where we have, there's a difference between the target that we're going after and maybe where other projects might be. There's a number of approaches to get there. We could just use off-the-shelf packages to do that, or we could create a code base from scratch. And of course, we chose to create a code base. And the reason why is because we really wanted to learn. And I don't think you really learn unless you really dig in. And I think, that'll become apparent as we walk through this process of thinking through what we've done. You really don't understand what the full set of choices are unless you get in and build every single little piece of it. So the process of digging in and building and presenting a possible solution to this problem is this project that we're working on here called OpenCBDC. So this is a C++ code base that implements a hypothetical CDBC. It's important to stress that this is not, the target here is not a production system. We're building a research code base to learn. And so that's what we've been building. We ended up with two solutions to that. And a system which we call the Atomizer, which reaches about 170,000 transactions a second. So we made it past our 100K target. And then a two-phase commit system, which does roughly about 10 times that amount. So we've been able to, find essentially some bottlenecks and present ways to maybe get around that. we're going to rely on cryptography. We're going to rely on a lot of things that we've learned across the industry lately. You know, over time, we've found that cryptography might be a good way to handle the identity in the system. So we're going to rely on that. We're also going to store as little as possible in the core, and that makes the system, you'll see, very quick. You're gonna notice that we try to strip away data as soon as possible, so we don't have to store it, and we don't have to keep it going. We really want to make that set of state as small as possible. We're going to parallelize wherever we can, right? And that's part of it. Like, how do you take the things that can be done in a parallelized way and just really parallelize it, and not have to create yourself essentially an artificial bottleneck, break the problem up essentially. But of course, across the whole thing, we really wanted a flexible framework. So we want something that we can experiment with many different ways. And I suppose you're looking at two of them here, the Atomizer and the two-phase commit, as an example of how this core platform is able to support two different, really very different ways of approaching essentially getting transactions settled. The goal here is to learn. We really want to, cast a wide net and understand all the possibilities and the options, all sort of what are all the dials and what happens when you turn them is essentially the goal here. So this, as you've seen before, is the GitHub link. This is where the project is. You'll notice there's the project is open source there. There are issues there and PRs and whatnot. And it's you'll hear a bit more about this at the end of the presentation from Sam Stewie at MIT, and he's managing the open source effort. And you'll find ways to get involved there. So that would be great. Okay, so what I'd like to do at this time is hand it over to James Lovejoy, and James will talk us through the deep dive of the OpenCBDC architecture. James.
Thanks, Anders. So yeah, I'm going to spend some time during the presentation now talking about the paper and sort of the main takeaways in terms of what we built, what the high-level benchmark results were. So first, I'm going to spend some time talking about the transaction format, so what the interface is that users would ultimately use to interact with the platform. Subsequently, the data model, so how the transactions are actually stored and processed within the system. And finally, talk about the two architectures that we built, the sort of primary differences between them, and then discuss the high-level benchmarks that we built. I'm going to take some time to take questions during this part of the talk. So after talking about the transaction format and the data model, there'll be some time to answer any questions that you may have. So feel free to post any questions in the Q&A. So starting off with the transaction format, what we ended up with ultimately was a Bitcoin-like UTXO-based transaction format. And a large part of the reason why we chose this is because a lot of the developers on this project have a lot of prior experience with Bitcoin, and we know Bitcoin's transaction format to be secure and fairly usable in a lot of different ways, particularly around flexibility for future programmability, and also the ability to interoperate with a lot of existing systems, which are areas of research that we'll cover in future phases of the project. So what that means is that the unit of account in the system is an output. So that consists of a value, the amount of money that the output stores, as well as this thing called a witness program commitment. And this is equivalent to a script hash. So we're taking some rules that we're going to use to lock up the funds to determine how they can be spent. And we're going to take a hash commitment of those rules and place them in the output. So transactions consist of a list of inputs, which is the money being spent in the transaction, the outputs, which are the new set of funds that are being created as a result of spending the inputs, as well as a list of witnesses, which are the input data to these witness programs in the inputs, which will determine whether a valid spend can be made of that output. So inputs spend unspent outputs. So some output that's previously been created and is present within the CBD system can be spent by citing it in a transaction, by adding the output data, so the value and the witness program commitment, as well as this thing called an output pointer or outpoint, which determines where the output can be found within the backend system. And finally, the witnesses are data that unlock the outputs so we can spend them. So this is going to contain the actual witness program itself, which is compared against the witness program commitment in the original output, as well as whatever data is required to satisfy that witness. And so as a result, there's one witness per input, which means that you can have different witness programs in a single transaction, meaning you can support things like multi-signature transactions, multi-party transactions, and so on. Similarly to existing UTXO-based cryptocurrencies, all the outputs in the transaction, all the inputs are destroyed in full, and new outputs are created to replace them. What's slightly different with our format versus what you might be used to is total value in the transaction must be completely preserved. We didn't implement fees in this phase of the project. So the way fees are usually charged in other cryptocurrencies is with a deficit on the output side, and the difference is given to the miners as fees. But since we don't have miners or fees, that's not required. So moving on, the next thing we need to talk about is transaction identifiers. And these are used to uniquely identify transactions within the system, which is particularly important for preventing things like replay attacks. So what we do is take the cryptographic hash of all the inputs and outputs in a transaction. And we hash that, and that gives us the transaction ID. And the advantage of this is because all of the transaction IDs are unique, it means you can use that as a signature payload when you're trying to validate a valid spend of an output. And it also allows us to uniquely refer to outputs within the system. So we simply take the tuple of the transaction ID we generated and the index of a particular output within a transaction, and we use that as the out point, which is how we uniquely refer to an output within the system. Importantly, the witness data, the witnesses are not actually included in the transaction ID. And this is important to support layer 2 platforms, particularly the Lightning Network, because it allows you to generate chains of transactions without authorization being included. And it also prevents malleability of the transaction, because it means that no matter how you sign a transaction, as long as you have the same set of inputs and outputs, you always get the same unique transaction identifier. So finally, on transactions, we can sort of put it together and end up with these witness programs, which are literally executable programs that define the rules by which an output can be spent. And so this is it's a function which takes some input data and returns true or false, whether or not it's a valid spend. And a great example of this would be a pay to public key program, which simply checks that the public key cited in the output has signed the transaction over all the inputs and outputs, so that the person who's created the output has authorized the particular transaction that's being proposed. A key takeaway is that we only store the hash or a commitment to the witness program in the output itself. So that blinds the actual witness program until there's a spend of the output. So the system doesn't actually know what the witness is going to be until you spend it. So that's useful from both a privacy and data retention perspective. So putting it all together, we end up with this example transaction. So in this example, it's a 2 input, 2 output transaction. We have 2 inputs of value 10 that were created previously. We have their out points listed, as well as the output data stating the value and the witness program commitment. And then we're going to create 2 new outputs from these inputs, splitting the 20 total input to an output of value 5 and an output of value 15 with their own witness program commitments. And then we need a witness per input, which is going to state the witness program. In this case, both inputs are paid to public key, and then we'd also specify the public key and provide a signature over the transaction ID of the transaction to prove a valid spend. So before I move on to discussing the data model and how that transaction format is actually implemented and stored in the system, I'll take a pause for questions if there are any.
James, we do have one question from the audience. What are the advantages and disadvantages of using a UTXO versus account balance model?
So I think there's one primary advantage of UTXOs over account balance is if you're going to be transacting with a single public key, because perhaps you're a large public entity that needs to issue a lot of transactions. With UTXOs, you can exhibit a lot more parallelism, because if I'm sending 1,000 payments to a single public key, I can just make 1,000 outputs to do that. And it doesn't require any concurrency control between the different outputs to issue those transactions. Whereas in the account balance model, if I have one account associated with a singular public key, I now have to sequence all the transactions. Let's say there are 1,000 of them with respect to each other, because they all need to access that account. So you get a lot more parallelism with UTXOs. I think the disadvantage is probably ease of understanding and ease of use for sort of developers and end users. With UTXOs, you need to scan the entirety of the ledger to figure out how much money you have, or use a block explorer or something of that nature. Whereas with account balance, you can simply look up the current state of your account to find how much money you have. So that creates a challenge in terms of transaction protocol, especially when, as you'll find out later in the talk, if you blind the ledger from people using the system, it actually becomes impossible to scan the blockchain or the ledger, so to speak. So it makes it very difficult to find out whether you've gotten paid.
Thanks so much.
No problem. Okay, so let's move on to the data model now. So previously we talked about the transaction format, which is how users and developers actually interact with the system. That's the transaction payload you submit. But behind the scenes, the way the system actually digests and processes those transactions is a little bit different. So what we ended up using is this data structure called an unspent hash set, which was actually proposed several years ago by one of the contributors to this project, Corey Fields. And the idea is to, rather than actually store the raw unspent outputs, so this map of out points, transaction IDs and indexes to output data, i.e. values and witness program commitments, instead you can just use hashes to store simply a commitment to the unspent output, and you require that the user provides the output data to prove that a particular output they're claiming actually exists as a commitment in this database. So, as said in the title, unspent hash set, what we implement is a set of hashes. And so in a transaction, we're going to have this two-step process. We're going to take an input, generate this UHS ID from it, and simply check whether a UHS ID is present in the UHS. And then to spend an output, all we have to do is remove the UHS ID from the UHS. And we generate a UHS by simply hashing the input data. So the out point, the TX ID and index, the value and the witness commitment put into, say, SHA-256 to generate a UHS ID. And so the UHS is a data store that really only implements one operation. And that is to atomically check that all of the UHS IDs that are being spent in a transaction are present in the set. And if so, delete the UHS IDs that are being spent and create the new UHS IDs that are in the outputs. And so if we do this atomically and durably, once we've generated this list of UHS IDs, inputs and outputs, that's really the only operation our system needs to support. So what we have to build from the full transaction that we made before is a compact transaction. So we're going to, for each input, just take the input data, hash it, and that will give us the UHS ID of that input. And then for each output, we're going to generate a hypothetical input. So If that output was to be spent in a subsequent transaction, what would the input look like? We just generate the transaction ID and the index of that output in the transaction, combine it with the output data to generate an input, hash that input, and that becomes the UHS ID that would be inserted into the UHS. So once we get this list of input UHS IDs and output UHS IDs, that's the actual transaction that's really getting settled by the system. So finally, we get to sort of the overview of the architecture, and this is true of whatever backend implementation you may end up using. A user has a wallet which manages their full outputs, all the output data. They generate a transaction using unspent outputs that they have available to them. They sign the transaction, and then they send it to a component called a sentinel. And so the sentinel's job is to check all the transaction local invariants of the transaction. So particularly that's the transactions well formed, it deserializes into a data structure that makes sense. The input values equal the output values, and it also evaluates the witness program for each of the inputs to make sure that each input that's being claimed to exist would be a valid spend with the given witness data. So if the sentinel validates the transaction and finds that it's valid, it converts the full transaction to this compact transaction by hashing the inputs and outputs to get the UHS IDs, and finally sends that compact transaction to the actual backend database to be executed and settled. So I'll take another pause there before we move on to the actual architecture description.
We do have another question. So somewhere in a similar vein around account balance models and UTXOs, does using the UTXO model prevent programmability in any way?
I think that's still to be explored. I think definitely an interesting area of research is to what extent does using a UTXO model versus an account balance model affect programmability. I think what's possibly more important though is this split between transaction local validation and looking up the state that limits programmability a little bit more. I mean, with UTXOs, you still get output scripts. So you have the ability to, validate that a spend is valid. So you can have very complex scripts, but what is more challenging to implement is this idea of, a state transition in the output. So in Ethereum, with the account balance model, you're essentially calling a function, and that defines the state transition that transaction is going to make. Whereas in sort of the UTXO model, you're more defining what the start state is and the end state is, and defining the rules of whether a transition can happen. But the extent to which that prevents certain features and primitives being implemented, I think is still unclear. But yeah, that's definitely something we'll be exploring in the future.
Another question, does writing this in C++ rather than a memory safe language raise any concerns, or given that's only for research purposes, it's not a concern at all?
So I think that in terms of the code base we built, we used the latest C++ standard that we could, which is C++ 17 at the time, and we'll continue to upgrade that to newer standards. And I think a lot of the modern features of C++ that have been released in the last few years really make C++ a fairly memory safe language. Like, yes, it's true, you can do pointer arithmetic and what have you, but you really shouldn't be doing that. And we have linting tools on our repo to catch that kind of, abuse of the language. Like, you shouldn't be writing new or delete anywhere in the code base. And I'm pretty sure in our own code, we don't do that. There may be, one example. So, although other languages can do some static analysis to figure out, memory violations, I think if you're just using the right primitives in C++, like really modern primitives, you don't actually need to be managing memory manually anyway. So you really shouldn't be having concerns like that.
Great, that's all for now. You can keep going.
Okay. So we've talked about the data model and the high-level architecture. So now let's talk about what we actually built to implement the backend database in this case. So the first architecture we designed, we call the Atomizer architecture. And the high level thinking here was to take the sort of distributed blockchain approach where you have a sequence of transactions in blocks that get executed one after another, and find a way to split up the various components of that and scale them out individually. So in the first step, as we discussed before, we have the static validation, we have the Sentinel. And obviously the Sentinel layer can be scaled out arbitrarily because it's not referencing any state, it's simply doing a static validation check on a transaction, generating a compact transaction and forwarding it on. So that's the validation step taken care of. But the next step is checking that a particular output is actually unspent. And that's what we use these shards for. So each shard stores a subset of the overall UHS. And then in the final layer, there's this component called an atomizer. And the atomizer's job is sort of the last main step of settling transactions in a blockchain system, which is actually ordering the transactions, including them in blocks, and then making the blocks durable and sending them out to the participants to apply the effects of those blocks. So the shards, they receive compact transactions directly from Sentinels. And their job is to check that the UHS IDs cited in the compact transaction actually exist in their view of the UHS. If a shard finds that there are inputs that exist in its UHS, it forwards the compact transaction to the Atomizer service and attaches a list of attestations where the shard is saying these inputs in the transaction are the ones that are currently present in my view of the UHS. The Atomizer is aggregating these compact transactions and input attestations and is trying to build compact transactions that have a full set of attestations. So an attestation for every input UHS ID in the transaction. If it finds such a transaction, it adds that transaction to a block, and then every fixed time period, it seals up the block and broadcasts it back to the shards. And once the shards receive a new block, they atomically apply the effects of that block to their UHS by deleting the input UHS IDs and creating the output UHS IDs. So how do we get fault tolerance in this architecture? Well, the Atomizer service itself is replicated as a raft cluster. So the compact transactions and the attestations that are coming from the shards, they get replicated as part of a replicated state machine before they get added to a block. In terms of the shards, multiple shards cover the same range of UHS IDs. So more than one shard stores the same UHS ID. If you split the UHS in half, you could have 4 shards where 2 shards each store the overall subset of the UHS. Shards also include the block height, which an input attestation is valid. So this prevents the problem where 2 shards are out of sync and are at different block heights, because the Atomizer is able to maintain a cache of recently spent UHS IDs so that it can accept stale input attestations from shards by checking in that cache whether or not a stale attestation is valid because it has the particular UHS ID hasn't been spent in a recent block. And finally, there's the Atomizer service. So the archiver service, sorry. So the archiver stores historical blocks so that shards can catch up to the most recent block height if they miss a block from the Atomizer service. So the archiver will communicate with the Atomizer to receive blocks, store them durably, and then allow the shards to retrieve those blocks at a later time in order to catch up if they need to, or alternatively to rebuild a shard from Genesis if that ends up being required. So that was the first architecture we built. And we ended up building 2 architectures because we quickly identified that this Atomizer service really represents a bottleneck in the system. In order to scale out horizontally, you really want to be able to add more machines to your system in order to support more throughput. However, since all transactions have to go through the Atomizer and be deduplicated and included in blocks, eventually you end up at a limit of that Atomizer cluster. And although you could scale by getting a better network or a better machine, ultimately it's much harder to scale vertically than it is to scale horizontally, simply because machine hardware is not advancing, at least in a single-threaded capacity, as much as it used to. So we wanted to build an architecture which didn't have this sort of central point of ordering. And the key thing to identify is that you actually don't need to order all transactions with respect to each other. If two transactions are occurring in the system that don't touch the same state, aren't interacting with the same people, then they don't need to be ordered with respect to each other, and they can be executed in parallel. So instead, we used a two-phase commit protocol-based approach where we have still shards that, same as before, store a subset of the total UHS. But this time, the shards have locks associated with each UHS ID. So an unspent output can be locked for a particular transaction. So compact transactions are sent from the Sentinel to the coordinator, and the coordinator runs the two-phase commit protocol between the shards. So it goes out and it tries to lock each of the input UHS IDs in the particular compact transaction on each of the shards. So if it receives a notification that all of the inputs to a compact transaction have been successfully locked, it can go ahead and proceed with the transaction. So it will then subsequently go and commit the transaction by telling the shards to delete the previously locked input UHS IDs and create the output UHS IDs. Alternatively, if one of the input UHS IDs couldn't be locked because it's already locked by another transaction, or it simply doesn't exist to be spent, the coordinator will find that out when it tries to lock the UHS IDs and subsequently abort the transaction when it realizes it can't complete, by telling the shards to unlock all of the input UHS IDs they've locked for that particular transaction. So what this means is that there's no central bottleneck. There's no sort of pinch point in the system. You can add as many shards as you like and as many coordinators as you like. And the concurrency control is done instead of by blocks and executing transactions serially. You can now execute transactions in parallel, and the concurrency control is done via locking on the shards, so locking the inputs. So moving on, the way we get fault tolerance in this architecture is similar, except now the shards are also replicated as raft clusters. So every RPC that the shard receives from a coordinator is first replicated in the replicated state machine before being executed and the response sent to the coordinator. And so if the leader shard in the cluster fails, one of the followers can seamlessly take over from where the previous leader left off. Similarly, the coordinators are replicated as raft clusters as well. In two-phase commit, there's a sort of classical problem where if the coordinator fails, any locked inputs on the shards will remain locked until something comes along and unlocks them. So by replicating the coordinator in raft, we can store each transaction and the state of that transaction as it goes through the two-phase commit protocol. And then subsequently, when the leader fails and a follower takes over, the follower can retrieve the state of all the transactions and complete those transactions from where they left off in the two-phase commit protocol. So it's a little bit more of a complicated fault tolerance story, but it ends up with a decent trade-off in terms of performance. So finally, if we take a look at the benchmarks that we ran just on a very high level, obviously, there's a lot more detail in the paper, and I really encourage you to read it. There's a lot of good stuff in there, but we tested both architectures in AWS in a multi-regional configuration. So we used 3 US-based AWS regions. We used Northern Virginia, Ohio, and I think Northern California or Oregon. And that was for fault tolerance purposes. So we really wanted to demonstrate that we could get performance in a situation where we could lose, one or more entire geographic region in AWS. So we used to benchmark the system a randomized 2-input, 2-output workload. So we generated millions of transactions. where we're spending 2 inputs that were previously created and creating 2 new outputs to keep the total number of outputs in the system balanced over the course of the test. And what we found is that as we increase the number of shards and the number of sentinels in each system, and also increase the load, Atomizer really reaches a throughput plateau. So you can see from the plot there, we were able to achieve the peak throughput with 8 shards in the Atomizer configuration, and we were really only able to get around 170,000 transactions per second out of the Atomizer. And that's because the Atomizer service ends up being a bottleneck. However, the two-phase commit architecture really seems to scale pretty much linearly with additional shards. So we tested the two-phase commit architecture all the way out to 32 shards. And with that, we were able to achieve about 1.7 million transactions per second. But it seems that two-phase commit would continue to scale. So if we did a test with 64 shards, I would expect that we would get even more throughput out of it. The main challenge there being, the scale of the test and the number of machines you need in order to run a test of that size. So in summary, what we really built, what I talked about in this section of the webinar is we built a secure transaction format and data model. So we employed a format which uses cryptographic authorization of funds transfer, which was really important from both a security and also a flexibility perspective. We didn't want to necessarily build identities into this part of the system or talk about whether intermediaries were required. So by using a sort of identity neutral cryptographic based authorization scheme, we're really able to remain flexible in that sense. The second thing is it really minimizes data retention. By using the UHS scheme, we're able to completely minimize the amount of data that the central bank would be retaining. And finally, the transaction format is both non-malleable, so it's useful for potential layer 2 and programmability applications in the future. And the format's also non-replayable. So once you've signed a transaction and you submit it, you don't have to be worried about the fact that other people holding that transaction can move your money. The authorization's a single time use. And then we built 2 architectures that implement the transaction format and data model. One of which is the Atomizer, which provides a linear global ordering of transactions, but ultimately peaks out at about 170,000 transactions per second. And then we built a second architecture, two-phase commit, which implements parallel transaction processing and appears to have no, at least from what we've seen, no experimentally demonstrated peak throughput. And so with that, I'll hand it back to Anders.
Thank you, James. That was great. And during your presentation, we got a flurry of questions. So let me quickly take a break here and maybe we can get to several of them. Nikhil, can you queue us up?
Sure thing, Anders. So the first question, James, for you is, how redundant is the data in each shard? Like what happens to the UHS if a shard goes down?
So it depends on the architecture. In the Atomizer architecture, you just want to make sure that there's always one shard node online that has a particular subset of the UHS. So as I said earlier, if you want to partition the UHS in half, you could have 4 distinct shard servers such that each half of the UHS is replicated twice. So you could lose any one of those servers and still keep a full copy of the UHS. And if one failure is not enough, you can add more servers to get a higher degree of replication and thus more fault tolerance. In 2PC, the UHS on the shards is replicated using Raft. So by adding more nodes to the Raft protocol, you can support a higher number of failures. And as long as over half of the nodes in the cluster remain online, then the UHS remains consistent.
Sense. The next one we have is, can Sentinel scale by handling the transactions in parallel? And can they detect and prevent denial of service attacks?
So yeah, so the Sentinels, the way you scale those is just by adding more of them. They are stateless components in the system, so they don't, require access to a database or anything like that. So by adding more of them, you can validate more transactions and digest more of them into compact transactions. What was the second part of the question?
Can Sentinels detect and prevent denial of service attacks?
Right. So in this phase of the research, we really didn't explore, rate limiting, denial of service, fees, and things like that. I think that's something we've left for future work at this point. But we have a number of ideas about what you can do at the Sentinel layer to prevent denial of service. Anywhere from sort of network-based, more sort of basic network-based stuff, all the way up to requiring a proof of work on transactions. I mean, fees is one option again, but it all needs to be explored, I think, in the future still.
Makes sense. Another one around UTXOs. So if a wallet has $1 in UTXOs and wants to spend $10,000, will the transaction inputs have 10,000 elements?
Yeah, I think, yeah. So if you had 10,000 single dollar inputs and you wanted to spend that into one single input, yeah, you would need to make either a 10,000 input transaction, or make a tree of transactions where you sort of slowly aggregate your inputs down into bigger, larger value inputs. But this is a problem in other UTXO-based cryptocurrencies as well. We've seen in Bitcoin exchanges especially end up with millions of inputs that they can't spend or would be very expensive to spend. So yeah, UTXO management is another challenge very much that people would have to deal with in this kind of data model.
Great. Next one we have is, does batch processing on two-phase commit create a window for double spend attacks in any way?
No, it doesn't. So both architectures completely prevent double spends. It's impossible to double spend if the system is correct. So with the batch processing, the coordinator is going to make sure that all of the transactions in the batch that it's creating are mutually exclusive before it submits them. And then if there are two coordinators that are executing conflicting transactions at the same time, the lock on the shard for that particular UHS ID will prevent two batches from spending that input at the same time. So that prevents double spends.
Great. I think we should move on if we can. Thank you very much, James. That was stellar. That was really great. I appreciate your time there. So the next section we have is an overview of the open source project. And for this, I'd like to hand it over to Sam Stewie at the MIT DCI. Sam.
Hey there, thank you, Anders. Okay, so there are two things I want to immediately talk about with OpenCBDC and the research project that we're starting. And the first thing is about what our actual goals are, right? And the most important thing, the thing we want to make sure we accomplish and focus on throughout the entire project is making sure we find relevant questions to ask about CBDCs and what they might look like, and try and come up with useful, actionable answers to them. And that means, among other things, it'll be helpful to have people brainstorming relevant questions with us, coming up with ways that we might find an answer to any of those questions we come up with. So that might be implementing proofs of concept in code, that might be running benchmarks or tests. There are a multitude of ways that people can help us out on that. And then we also need to try and really carefully evaluate what the trade-offs, both positives and negatives, of any particular designs are. To that end, I should try and make sure to mention the two designs that we've implemented so far are not like the designs. These are just two we've explored so far. We are absolutely interested in exploring other designs. And one of the things for evaluating these trade-offs, we found that there are a lot of frictions in our current payment system. So if we have the opportunity to potentially build, as a society, build new currencies from scratch, what trade-offs can we make in these designs? What positives could we could we garner? And we're not entirely certain that CBDCs could get us, the greatest pies in the sky. But that's part of what this project is hoping to try and answer. So to that end, we want to invite everyone to collaborate and contribute with us. And we've posed this particular way of trying to organize research. So anyone who wants to contribute to the project is able to open proposals. And I'll talk about a little bit how you'll do that later. And those proposals can range from very specific questions like a small bug fix or a change to an implementation we've done so far, or a performance improvement, to something much larger, like a new design or architecture, or something we haven't considered before. Once those proposals are made, we're going to organize working groups. And these working groups are going to be focused on evaluating the proposals and prioritizing them so we can come up with kind of a research plan and move forward on implementing any of these solutions, trying to find answers to these questions posed. And finally, we'll have a set of maintainers that are focused on curating and merging any solutions which help further the research goals of the project. So moving on, I think it makes sense for us to kind of talk about where we'll go next. That's great. We came up with a model for how you can contribute. Where do we start? The obvious thing that jumped out to us is privacy. So the first working group we're going to kick off, and we'll actually be kicking it off next week, is working group 1, privacy, auditability, and compliance. The questions listed here, by the way, are not posed in any particular order. They're not in level of importance or anything like that. These are just some of the questions we expect the first working group to try and answer. So, how much data does the transaction processor actually need to store? And for the purposes of only processing a transaction, our current designs suggest not all that much. But our current designs don't necessarily answer questions like, how do you audit the system? Or how do you make sure you comply with any compliance mechanisms a jurisdiction might need? So as we try and tackle any of those particular challenges with auditability or compliance, what new data do we need to add to the system in storage? And if we do, what does that reveal? What are the trade-offs of doing so? Obviously, having the system be auditable is something that's going to be incredibly important. So what kinds of auditability can we actually support in a system like this? What level of privacy can we assure for people transacting with the system, and from whom and for what kinds of data? We're not entirely certain about that yet. These are all still open questions. And then, kind of finally, I say finally, there are so many more questions in this space to answer. But finally, at least for our examples, what mechanisms of compliance actually are possible for us to implement? And what might those look like? And if we implement any of these, are there fundamental trade-offs, for example, in performance that we might garner? And we're not really sure yet. And there are probably a lot of other questions too. I suspect many people have more questions that are not addressed here about how privacy or any of the questions that flow from privacy, like auditability or compliance, would work in any CBDC. If you find yourself asking more questions, please feel free to open a proposal. So there are a bunch of different ways you can contribute. The first one, kind of the obvious one, is that this is an open source project and our repositories are available. Please feel free to dive in. I think right now we have 26 issues open on the issue tracker. They range in level of difficulty from some things that are kind of open-ended questions to some things that are really easy for you to jump in now. Please feel free to pitch in a hand. Obviously, the second thing you can do is sign up to join a working group. By the way, that form in the middle, if you sign up for it, you'll not only be getting any updates to working group meetings or things like that, but any other presentations we have in the future like this or other webinars, we'll also make sure to send to that listserv. So if you want to stay up to date on the project, that's a great way to start. And then finally, the obvious one, you can submit proposals. If you want, or if you have an idea that you think the working groups should evaluate, we have a built-in form on our issue tracker for you to submit a research proposal. The URL is somewhat ornate, so we've made a nice little QR code for you here and then a short link for you to follow to make that easier. In general, we're going to try and focus on presenting proposals at the working group meetings first, and walking through them and evaluating them. So if there's something, if you'd like to join the first working group and join us for our first working group meeting, which will be next week, the 16th at 10 a.m. through 11 a.m. Eastern, please make sure to submit a research proposal first, and we'll try and curate those proposals before the meeting starts. And then obviously, if you have any other questions, please feel free to reach out to us. If it feels like it's related to the code or you have a specific question about any of the technical aspects of the project, please feel free to open an issue on the GitHub issue tracker. But if you have anything else that you'd like to talk to us about, please feel free to email us at opencbdc@mit.edu. And then I think we should probably move on, and I'll go ahead and pass it back to Anders so we can kind of dive into the question and answers.
Absolutely, and if any of these, the sheer number of questions we have is any indication, Sam, your hands will be full. So look forward to doing that. Nikhil, let me hand it over to you, and maybe we can open up the Q&A session here.
Yeah, that sounds great. Maybe Anders, you want to stop sharing screen and we can just bring the panelists into Spotlight while James joins. Sam, this first one's for you. Why did we choose to make this project open source?
Oh, that's such a good question. Okay, so there are a bunch of different reasons we chose to make this an open source project. One of the obvious ones is just because by having the code be open source and allowing anyone ostensibly to contribute, we can get new ideas and proposals and designs from people who we otherwise might not have been able to. There are also obvious benefits, like more eyes on the code means we can probably fix bugs faster or find issues more quickly. But the overall thrust of the thing is that more people involved means better research, and that's what we're focused on.
Makes sense. Anders, this one's for you. Why did we choose to implement a completely new system from scratch instead of taking an off-the-shelf solution, like a high-performance blockchain, for instance?
Yeah, that's a great question. So really comes down to fundamentally different goals between the different systems. We believe that CDBC has a very specific goal set that's different from what others. You learn a lot by building things. You end up making like lots of little, thousands of little choices that add up directionally to provide the goals that you're looking for, and you can find a lot of efficiencies that way. The other interesting thing is you run across these interesting design decisions kind of somewhere in the project that maybe weren't quite so obvious up front, and that sort of does help inform the design space and maybe even direct future research where what you should be looking at. Again, this is a research project. It's not. This is certainly not something that is built for production at all. It's built to learn and be flexible. And so, having something with a lot of flexibility was really a main goal here. Yeah.
Makes sense. And thinking about the future and flexibility, is quantum computing a fear for the security of OpenCBDC at all? Like, what have we done to combat security issues due to quantum computing?
Yeah, absolutely. So this is obviously if there were some kind of a quantum issue, it would impact really the wider world, not simply a cryptocurrency or something. But I do want to drive home that, of course, this is research. This is not a production system again. So that said, though, we've decided to bring in very few libraries, one of which is a cryptography library, and we could swap that out. So the intention, I think, if this became something we wanted to study, and certainly future research in this area is necessary, we would want a very flexible system to be able to do that. And I think the way that you do that is you would swap out the library and rerun the tests and see what the impact is.
Makes sense. Switching gears a little bit, and James, back to you. We've got a lot of questions on the architecture. Is there a limit on the number of witnesses? Does the number of witnesses impact performance in any way?
So At present, there is not a limit on the number of witnesses. I think in practice, you would likely need to have one, but rate limiting in general is something we need to explore, I think, is in the future. Obviously, if you have more witnesses, that's more work for the Sentinel to do. That's not necessarily a problem, of course, because you can pretty easily scale the number of Sentinels to accommodate that. But then there's sort of like a resource utilization question, you know, how much money would it be costing the central bank to execute, you know, a really high number of witnesses or DOS the system. I think the other component to it is, you know, if you have a lot of witnesses, you also have a lot of inputs. And I think that's the thing that ultimately costs. You know, if you have a transaction with 1,000 inputs, that's a lot more coordination. You know, you may need to touch every shard potentially in order to execute that transaction. So I think witnesses are probably less of the problem, and it's more likely to be the number of inputs that would have to be limited. But yeah, I think in the future, you know, you would need some mechanism to at least make it cost more to transact with a higher number of inputs to sort of disincentivize that.
Makes sense. Another question we've gotten on security, and now James and Anders, I'll let you pick who answers this one, but how can OpenCBDC be secure if a hacker gets into the shards database?
James, do you want to attack that? I mean, basically, let me just preface it by saying, again, this is a research system, not a production system. That's not really the area where we've focused yet. Certainly an important area. James, do you want to talk about some of that?
Yeah, I think, you know, adversaries getting access to back-end components of the system was not something that we seriously considered as part of our threat model in this phase of the research. But I think that is something to look at. I mean, as was mentioned earlier, you know, we didn't go with a Byzantine fault-tolerant based design simply because in our threat model, the central bank runs the CBDC components, and it's assumed at least that it's very difficult for an adversary to get across that boundary. However, if that, you know, turns out to be a part of the threat model, then yeah, you would have to explore different techniques for auditability, tamper detection, or even, you know, a Byzantine fault tolerant model that's able to detect those things. That being said, it's all very well having a BFT based component, but if you're all using one implementation and the adversary gets into the system via, you know, a bug or an exploit, that's going to apply to all of the nodes in your system. So, you know, BFT only really works if only 1/3 of the nodes can be compromised. So I think that there's like a lot to unpack there and a lot to explore, and it's something that we'll be looking at in future phases of the research for sure. Yeah,
I should just mention real quick that that's some area of active research. We've been trying to unpack the sort of the universe of issues here. It's something we've discussed quite a bit actually. We're not releasing research in this area yet.
Our paper also mentions like billboard transactions, like where the receiver isn't present. Are there certain transaction types that are difficult to do with these architectures?
Well, yeah, so absolutely billboard is one of them. There are ways to solve that. And I think, again, active research, certainly an area where we could go. James, I saw you unmuted.
Yeah, I mean, I think that the challenge in general comes from the fact that unlike, you know, decentralized cryptocurrencies, the ledger is not public. And so in you know, a regular cryptocurrency, the way you find out if you've gotten paid is by scanning the entire blockchain to find outputs that you're able to spend. But in this case, where we wanted to make sure that, you know, user-to-user privacy is a feature of the system, you obviously can't do that. So as a result, paying someone is an interactive process. You have to tell them that they got paid and give them the output data in order to spend their new output. So anything that requires that, it's challenging, but I think there are solutions. I mean, on the most extreme end, individuals may be able to do interactive communication. Like if I'm running some software on my computer and someone else is running it on theirs and we're able to communicate via the internet, that's fine. If people aren't able or willing to do that, there's a potential for, third-party service providers to, do this task for you of storing this output data and communicating with others in order to allow you to send money. That being said, this is just one data model that we've explored so far, and 2 architectures to implement it. And I think in the future, we'll look at other data models and what the trade-offs with those are for sure.
Sense. How does this architecture apply to a 2-tier distribution model? In the 2-tier model, the central bank is responsible for issuance to a small number of service providers, and these service providers distribute to end users. Is that how you see it?
Well, so that's I think quite a bit more nuanced thing than simply a binary A or B. That can mean a lot of different things. And of course, you want to build a system that's flexible to be able to test each and every one of them from one end all the way to the other. So some of the things actually are just exactly what James was just talking about. You can have an intermediary come in to kind of handle some of the issues like sharing output data around or remembering output data for people or something like that. All the way through to obviously a completely intermediated system as well. These are, it's a pretty wide design space.
Thanks. We still have a bunch of technical questions coming in, but I want to group some of the open source related questions that we've gotten as well. So Sam, these ones are for you. What kind of contributions are you looking for? And do you need to be an engineer to contribute to a working group?
Oh yeah, okay, sure. Yeah, okay, let's answer both of those. All right, so we're looking for so many different kinds of contributions. Probably the easiest thing to say as a shorthand is that on our issue tracker, we've gotten somewhat specific with our issue labeling. And if there is a label that exists for the kind of contribution you want to make, we're probably interested in receiving it. And that goes from everything to like bug fixes, to performance enhancements, to documentation improvements, to new architecture proposals, right? Much bigger things. Feel free to just open one of those contributions, any issue if you'd like to contribute. As for participating in a working group, no, you do not need to be an engineer to participate in a working group. Having said that, it's worth mentioning that the first few working groups we plan to launch are focused very specifically on technical questions. And that means I'm not quite sure how interesting they will be to a non-technical audience. But you're absolutely welcome to participate and join. And I should also dovetail from that as well. If you're feeling not quite so confident in your ability to contribute technically, like I said, there are things you can do on the code, like improve our documentation, that would be more than welcome. We also, one of the things we label our issues with is how difficult they would be to actually implement, or our guess on how difficult they would be to implement. And so the kind of lowest tier of that is like good first issues. And I believe we have about 7 of those open right now, and we'll continue to open those as we see them. Those are probably a great place to start if you want to try and get your feedback.
Thanks so much, Sam. I'm going to pivot back to some of the technical questions again. So James and Anders, this one's slightly long, so bear with me. Does the system require that users store all their outputs and present them when they want to spend? What's the user experience going to look like for those who can't store all their unspent outputs?
Yeah, generally, I believe the sort of the user research piece is really not there and needs to be really explored. And just if you think about it, obviously though, that's a clear problem right there, right? That's something where an intermediary could certainly help. That's a pretty kind of carved out problem that an intermediary could address. And yeah, I mean, it's mostly to be explored, I think, at this time. Open issues, really.
James, anything you want to add there?
I don't think so. No, I mean, yeah, it's a challenge, as we said before, of having the ledger not be public. Someone has to store this output data. And whether it's you as an individual or a third-party service provider that does it is a question that would need to be answered. But yeah, you would definitely need a solution for that.
And let me just answer, add a little bit more there. There's been some talk amongst our team, like, how do you handle this issue? Can you shuttle the information around in an encrypted way that the person with the ability to spend can get it? I mean, you could imagine a system of shared output data like that that would be built. And so, like, that sort of implies that there's specification there. How do you get that stuff? Where is it stored? Who handles it? Like all of that. I think that's probably a pretty big space right there, just as the user research is also a very big space that needs research.
Moving on to the next one. When a user receives funds in a transaction, do they have access to the whole transaction data so they can see the amounts of the spent inputs or guess the change in values?
So no, they don't. Yeah, so that's one good feature about the transaction format is, let's say I'm making a very large payroll transaction where I've got many inputs and many outputs. In order for me to spend my output as a recipient of that payment, I only need the output data for my specific output. So I don't know anything about the other outputs in the transactions, what the total value of the transaction is. I just learn about my singular one output.
Great. So, sorry, the questions are pouring in, trying to figure out what's next. Is it correct that the transaction history will be maintained outside the core system?
So it depends. So the Atomizer architecture does store the block history. So there is some record of the transaction history, but even that only contains compact transactions. And the 2PC architecture doesn't maintain a history at all, at least right now. So yeah, it's another place where a third-party service provider, whether that be actually providing a platform or just software to actually manage someone's transaction history and provide it to them, because the central bank in this design doesn't currently retain it, and thus there's no block explorer, right? There's no way to go and look up a historical transaction or someone else's transaction, so someone else would need to store that if you wanted to retain it. Makes
sense. Shifting gear to minting and issuance, Anders, this one's for you. Like, how is minting and issuance done in the system, and how is it securely handled?
Yeah, so that's a great question. So in short, it's not, it's not really, we haven't dug into that research, but we absolutely need funds to be able to test. So the question, I suppose, is, well, how do we do it right now? Well, the way it's done right now is not the right way, right? So we precede the shards with the output data that they need to be able to run the test. That said, though, this is a really interesting area. I'm very excited by it. It's probably there's a large design space there that not only includes the technical possibilities in how you would handle minting and burning, but also operationally. You want to have some kind of a friction there, probably both supported from the technical realm, but also in an operational space to really answer that and handle it well. That's a very, very interesting area that I don't think we've really scoped out yet. I mean, I'm excited by it. I think it's really interesting, but very, very difficult to do right.
Definitely. James, why did we use Schnorr signatures instead of BLS signatures?
So I think there are a couple answers to that question. The first is that there's been a serious standardization effort surrounding Schnorr in the last couple of years. We've seen it most recently getting adopted via Taproot on Bitcoin and on a plethora of other projects as well. And so what that means is, we have a very robust implementation of Schnorr available to us, which is a library that we used in the code base. And the second thing is interoperability. So given that other projects are using Schnorr, there's sort of one unified signature scheme that can be used across a lot of different projects and platforms. And Schnorr allows a lot of interesting features surrounding privacy and also things like multi-signature and scriptless scripts and so on. BLS is I would say, a lot less explored, at least in the cryptocurrency space. And so it's something we could use in the future. Our transaction format would allow for any number of signature schemes or different script types. So if someone really wants to explore, using BLS signatures, then, we would accept a PR for that and would be interested to see what you can do with them for sure.
Yep. We've got a couple of questions around programmability and smart contracts that have come up again. So do we need a linear order to implement smart contracts? And are we planning to explore this more in subsequent phases of work? Maybe Anders, we can get you to answer this one.
Yeah, sure. I'll jump in first, and let's open up to James for comments. So, do you need a linear order? I don't know. I think we should figure out whether or not that's required or not. It doesn't seem to be. So that's something to consider. And then the question is like what makes it easier for somebody working on a smart contract to build something? Do they does a certain way that the system is built cater toward some programmability or another or not? Right. So those are some of the other things that you might consider. There could be interesting ways, certainly in the 2PC world, where you use the ability to lock across multiple things to, in turn, execute contracts or something like that. But that it remains to be seen what you can and can't do there. James, you want to talk about that and maybe what we're exploring in phase 2?
Yeah, I think I would be willing to go a little bit further and say that I don't think a linear order is required to implement, Ethereum style smart contracts. What's required is more complex concurrency control. So with our existing architecture, there's a complete split between transaction validation and execution. Whereas in reality, what you need for, an Ethereum style smart contract, at least, is this ability to do some execution, do some validation, then go back to the database, query more data, retrieve it, do some more calculation, and so on in multiple rounds. And by extension, you really want to be able to call other smart contracts as well and have interactivity, at least on the platform, between different contracts. And all that requires is some form of concurrency control. So I think for phase 2, we've started exploring a third architecture based on 2PC, which has that capability. And the ability for more free-form smart contracts. So I think that's something we'll definitely continue to look at for phase 2 and understand the trade-offs, particularly in terms of performance, but also sort of security and expanding the attack surface of the platform pretty significantly.
Right. This one's on witnesses again, James. What's the difference between the witness and the witness program? And are witness programs as powerful as smart contracts? Like, could that be part of a system to be extended to work with something like an EVM or other runtime?
Right. So a witness program is equivalent to a script. So what a witness program does is validates that a spend of a particular output is valid. So it's going to take some input data and simply return a true or a false, depending on if the spend is valid. The witness is a field in the transaction where you provide both the witness program and the input data to the witness program for it to evaluate, hopefully to true. And then the witness program commitment is the hash of the witness program, which is what's actually stored in the output. And that's equivalent to a script hash. So in terms of whether those can be extended to support something like EVM, My guess is that they probably couldn't. This comes back to an earlier question we had about like how do UTXOs and output scripts limit programmability? And I think that's a research space that really needs to be deeply explored. But my guess is that it probably couldn't, simply because the output script is really limited to just validation of a valid spend. Whereas something like EVM is much more about defining the actual state transition in the code, rather than checking whether a particular state transition is allowed or not.
I'm going to pivot back to you, Sam, on some open source questions again. Are we going to have a Slack channel, Stack Overflow, or some other form of developer discussion beside Git issues?
That's a great question. So we don't have plans for that completely nailed down yet. I can tell you we're setting up an IRC channel. So people who are familiar with Internet Relay Chat would be welcome to join us. We haven't yet set up a Slack channel or a Discord or anything like that, but we are open to it. If you feel like a particular way of setting up communication with us would be helpful, reach out and let us know. Part of the wonder of an open source project is that contributors get to have a voice in how it moves forward.
And maybe a contributor sets one up for us.
Sure, yeah, there's no problem with that either.
Is there a way, Sam, while we have you, is there a way for other central banks to contribute to Project Hamilton and OpenCBDC?
Well, so Project Hamilton is kind of the collaboration specifically between the Boston Fed and MIT. So I'm not quite sure how that would look. But absolutely other central banks are welcome to participate in OpenCBDC. And the primary way you do that is by getting involved with MIT in a collaboration agreement and join us in the working groups. And then we'll just try and make sure that the questions the research project is focused on are, again, relevant to the kind of answers you'd need if you were to explore creating a CBDC for a production system.
Okay. We have a question that kind of ties to the working group, but it's on confidentiality. So it seems like the transaction data is public to the nodes. Is confidentiality part of the design, and how is that going to impact throughput?
Yeah, it's a great question. So as Sam laid out, the privacy working group is really, I think, going to be targeted mostly at that. There's many things to say about that. I think it's possible the Sentinels could use zero knowledge proofs to blind transaction data from the Sentinels. But there's quite a bit there, a lot of concerns and a large design space there. So there's the advertisement, Sam, for working group number 1. I think that's a super interesting area.
On the topic of the design space, right, for working group 1, are we considering zero knowledge proof-based protocols such as Zerocoin or Lulantis, anything of that sort?
Sam, do you want to jump in?
Yeah, so I would say first of all, we're open to any designs that you would like to propose. But our kind of initial thoughts on how we might go about some of our privacy goals that we'd like to figure out if they're possible to achieve definitely involves using zero knowledge proofs and seeing how we can leverage them effectively to try and blind information from ideally everyone, but again, still offering the possibility of auditability.
Unfortunately, we're also at the end of time, but I know we didn't get a chance to get through all the questions, but thank you so much, everyone, for submitting them. Thank you all for attending. I think at peak, we had about 170 people. I might have miscounted, but that sounds about right. Yeah, we hope many of you will contribute to OpenCBDC in the next coming days or weeks. And if you have any more questions, feel free to email us at opencbdc@mit.edu. Thanks so much, everyone, for coming. Bye now.